Give me a second. I will pause the recording and I will come back again. Just give me a minute. So once we have this, good overview of how a chip starts from a requirement analysis to finally shipping, we enter into this detail of how does the design implementation happen. Okay. So the first stage of the design implementation is initial design entry, where you say that, okay, I need this kind of memory, I need this kind of a processor, I need this kind of interfaces, DDRs, and so on. And then you do a design entry. This design entry is in RTL. Okay, you write a Verilog code, and that is RTL. Once you've done the design entry, you need to verify that this design is meeting the functionality that you wanted it to meet. So you simulate the RTL and do a quick power analysis that the power budget is also within the specified range. After that is done, you do the logic synthesis. Now, what do you understand by logic synthesis? There was already a question earlier about logic synthesis and layout. So what do you understand by logic synthesis?
It is mapping our RTL code to the gate level net list, the connections between the gate interface.
So it is converting an RTL Verilog netlist into a gate level netlist. That, okay, you just said an adder, but an adder is implemented by using these kind of ANDs and ORs and XOR gates. Okay, so that implementation is synthesis. After the logic synthesis is done, you do test and clock synthesis. What do you think test and clock synthesis entails?
Sir, so like when we test our code, like when we're simulating, so you're using a clock signal that you have provided, but to actually generate a clock which will run in that system, you need to do a clock synthesis as well. Like, okay, I mean, it should run at 2.5 megahertz or so. So yeah, I mean,
so let us look at it like this. In the logic synthesis, you said you will put 1 million flip-flops on your chip. And for every flip-flop, you simply put the clock pin. Am I right?
yes.
In reality, clock will be generated by some PLL somewhere, or you will get it from outside your chip. So there is one point on the chip where you will have the clock generated. And do you think that one point can drive all the 1 million flip-flops? No.
So we have clock buffers, right? I mean, in case
yes.
of confusion.
So you have to now arrange and organize these flip-flops in a particular way that, okay, these 10 flip-flops, this buffer would drive. These 10 flip-flops, another buffer would drive. So this part of inserting clock buffers, so that none of the clock pins or none of the clock signals nodes has a load more than, let us say, 100 femtofarads. Additionally, all the matched clock nodes, clock ends arrive at almost the same delay. So if there is one flip-flop and another flip-flop which were supposed to work simultaneously, it should not happen that because I put 10 buffers in one path and 5 in the other path, one flop operated much faster, much earlier than the other one. So if they were expected to operate synchronously and simultaneously, I have to put 10 buffers on both the paths. So this is clock synthesis. Similarly, as we talked about, initial functional specification and test specification, we look at test synthesis, that as to how will I make those scan chains? How will I test the entire chip once it is fabricated? So at this early stage itself, when you just at the logic synthesis stage or just right after that, you start to also do the test synthesis. You start to insert some test features also. Raghav, you have a question?
Yes, sir. Sir, in this clock synthesis, are you referring to the clock tree synthesis?
Yes.
And so one more thing. So like after the design entry, you have mentioned the power analysis. So but like design entry is in the RTL form. So we still don't have a kind of the components that will be involved. So what kind of power analysis that we are doing here? Like, how would we know that
Okay.
what kind of power can be
So
consumed?
let us say I said that I will use a memory somewhere. Okay. And I have not gated the access to the memory. So memory, every clock cycle, memory is being accessed. I know that a memory will consume more power. I have models for memory also. So in that case, then what we see is in that case, what we see is that the system will show that the power consumption is high, that you need to do power gating at some places to reduce overall power consumption. So you can change your RTL so that clock gating happens and memory is not accessed every cycle. It is only accessed when needed.
So, but my question is, so like RTL, at the RTL level, we are having only a behavior model. So like,
Yeah, but okay, so it is not just behavioral model. So the models that you have, the Verilog models that you have, many a times they are also associated with some top level information on power consumption and timings.
okay, like apart from the netlist also.
Yes.
Okay.
Okay.
So
Yes,
it's a kind of a basic doubt. So when we are talking about designing a chip, and all, are we talking about ASICs or
I'm sorry, can you please repeat?
are we talking about ASICs when we are talking about designing a chip? So
It could be an ASIC, it could be a ASSP, it could be anything. It could be a standard product altogether, a commodity product. Not even an ASIC and not even an ASSP. It is a standard chip.
okay.
Anything.
Okay.
So you know the difference between ASICs and ASSPs and standard chips?
Yes, sir. Yes, sir.
Yeah.
I mean,
So
I don't know what you're referring to by standard chips, though. I mean,
So
I know
like for example, Atmel Atmel 32 processor is a standard chip. It is available off the shelf. Anyone can come to the market and purchase it. STM32, it's a standard chip. Anyone can come. It is not defined or prepared for a particular application. Whereas,
okay.
for example, Chorus is a product from ST, which is a specific chip for automotive industry, but it is again standard. It was not made specifically for Bosch. It was not made specifically for Rolls-Royce. It was just made so that any user, any car manufacturer can use it. Okay.
So you're saying that it's like programmable. It can be programmed as to the needs of the customer. But
No,
then
it's not
what's the
about
difference between
programming.
that and
No. It is not just about programming, Meher. It is about application. For example, STM32 is a standard product. It would be used across any application. Whether you use it in a car, you can use STM32. Whether you use it in your Alexa, you can use an STM32. Whether it is Google Home, you can use STM32. Any application can use STM32. Even your smartwatch can use STM32. Okay. So any range of applications. It could be automotive. It could even be a satellite. It could be using STM32. So it is off-the-shelf available standard product. However, when I'm talking about, let us say, an automotive specific product, then that product is designed for a particular use inside cars only. For example, tire pressure monitoring sensor.
yes.
Now, TPMS you will not use in your watch, will you?
No.
It will only be used in automotive sector. But
Right.
it is not designed specifically for Bosch. It is a standard product. So it is application specific standard product, ASSP.
So, but like the features are somewhat the same, right? I mean, okay, you can only do these amount of things in this chip. I mean, and those amount of operations can be used in a car or in a watch or anywhere, but it's still fixed, right? You cannot change it. You cannot it's not field programmable like FPGA.
Yeah, for example, so that is that there are multiple flavors of, let us say, STM32. Some flavors would have 1 kilobyte of non-volatile memory. Some flavors would have 32 kilobytes. Some would have 1 megabit.
Okay.
So that will limit what all you can store and what all. So that would change stuff. But otherwise, it is STM32. It is a standard product.
Okay. Right. I understand.
Okay. But ASSP is application specific standard product. Now, tire pressure monitoring sensor is a Tire pressure monitoring sensor only. Any tire can use it, but it is specific to tire pressure monitoring.
Yes, sir.
And then there would be specific chips. For example, there will be a chip that Tesla orders, which says that I want a chip for car vision, so that I can go into self-driving cars.
Okay.
I want to use this particular algorithm so that it is most efficient for my purposes. Now that chip is an application specific IC.
Yes.
It is made specifically for one customer.
Okay.
It is much costlier for that customer, but customer may still want it for the competitive advantage.
Yes. Okay. Okay. I see.
Sir, sir, please explain logic synthesis again.
Logic synthesis? Okay, I will do that. Rajnish, you were also saying something?
Sir, as you were saying about the STM32, sir. Sir, basically, what you are telling is just like the work of an microcontroller. Sir.
Yes.
So, sir, is it a microcontroller?
Yes, STM32 is a microcontroller.
Yes.
Okay. So, Prashubh,
Yes, sir.
logic synthesis involves, so RTL would say that, okay, move data from register R1 to R2, add R1 plus R2, whatever, something like this. But how would you move data? You would need to have some buffer somewhere.
Yes, sir.
How do you add two numbers? You need to have that propagate and generate thing coming in. You will have to have something coming in to add two numbers.
Yes, sir.
So what would those gates be?
So
RTL is almost like English language. But finally, silicon cannot understand English. Silicon would understand only some transistor language. No?
Okay, sir.
So we don't even go to transistor language when we do logic synthesis. We go to gate language. So we come to arrive at a gate level netlist. We say that, okay, after this NAND gate, we will put an OR gate. And when these two NAND gates outputs connect on this OR gate inputs, the output of this OR gate is going to be A plus B. That A plus B I need to now write into that. So we will convert all those Mealy machines and Moore machines and everything. And that is what is logic synthesis. So implementing your English language or a program code into a gate level netlist. Is it clearer?
Yes, sir.
So you do this logic synthesis, then you do test synthesis. Once all that is done, you know what kind of circuits and what is the total number of cells you need to put on your device. You enter into a stage which is called as floor planning, as to where would you put your processor, where would you put your memory, where would you put different parts of your chip. Okay. I want the memory to be as close to the processor so that there is no delay in accessing the memory. One could say that. Someone would say that I would want to put the PLL on this corner of the chip so that it does not encounter any noise. Someone would say I want to put ADC on this place. So that is floor planning. You're basically building a plan of how you would lay out your chip finally. Consider it like if you have to build a residential complex. You need to plan where the 5 towers or residential towers have to be, where the swimming pool has to be, where the clubhouse has to be, and so on. So that is what is like floor planning. And after while the floor planning is done, you also do stuff like power estimation, static timing analysis, gate level synthesis, and so on. Gate level simulation, and so on. So what does static timing analysis entail? Who will tell?
So we
So
check
it's
that
timing
whether
verification.
the timing constraints are being met or not, the setup and hold constraints.
So
Timing verification. So
Yeah,
timing
flip-flops,
verification.
you know that flip-flops would have some setup time, some hold time, something. So when the clock arrives, the data should be set up. So whether that is happening or not, do you need to add some delay somewhere? So it is largely timing verification, timing characterization. Gate level simulation is once I've removed the English from A plus B and I've actually put an adder there, after all that logic conversion, is my netlist still operating the same way as I intended it to be? Okay. Then test structure verification is, I wanted to have a scan chain built there. I wanted to test different components independently. Am I able to really test them? Then power estimation. Now, since you have real gates available there, okay, you have real gates available there, you actually can estimate what kind of power consumption will happen. And then you also check that, okay, ऐसा तो नहीं हो रहा that there are two outputs driving one single node. So, or that there is some input that is floating, or that there is a load on a particular gate which it cannot even bear to hold. So all these checks you do. While you do these checks and as you complete these checks, you also release your netlist, which is now reasonably stable because it has met all these logical standards, to the layout. Now you say, okay, this was where I wanted to put my tower 1. This was where I wanted to put my tower 2. Now is the time to build the towers. Okay. So now you will start to place the windows, the walls, and everything over there, and this is what you would be. This is the final shape of a residential complex. And layout is essentially the final shape of your design. So you start to put the layout of the AND gate as to how it will appear on silicon. You put the layout of the NOR gate, of the adder, of everything, of the memory. So all those things you now start to put together, and you now do timing driven layout optimization. That, okay, the output of this AND gate is going into this OR gate. So let me place this AND gate and OR gate together. Okay. So that is layout driven timing driven layout optimizations. Once you've done that, you again need to do static timing analysis, because now you now know the additional information of how long a wire is there between two different gates. Till now, you only knew that this NAND connects to that NOR. Now you know that when this NAND connects to that NOR, there is also this long wire in between them. So the delays would change. And you need to do a timing analysis all over again.
Sir? Yeah,
Yes.
so, I mean, so the static timing analysis we did after the floor planning, we were not taking into account the routing delays.
So you would use some model, Meher, there. You would assume that, okay, most of the wires, like you will use a statistical model based on your earlier analysis. Some other chips you had designed. So you know that, okay, most of my wires were 1 micron in length, and a few wires were 10 microns in length, and very few wires were 100 microns in length. So based on that, you will statistically distribute those wire. So this is called a wire load model. So you distribute those wire loads on some different places, and you would do it. But now you actually have the real wire length available with you.
Okay. Okay.
So this is a more realistic analysis. So you do STA all over again, and you do post layout technology checks now. That is DRC clean, is LVS clean, is every gate connected to or every poly connected to a diode or a drain somewhere. Otherwise, there could be antenna violations, and the chip would fail after fabrication, and all that stuff. Okay.
So, the thing you said about if it's connected to the drain or diode wasn't it a part of gate level simulation? Like
No.
you have synthesis.
Diodes are not. Diodes have no functionality per se.
So yeah, how did we skip that in a gate level simulation? Because the whole
diode is
point
not
of
a
it is
gate.
that now
Meher, diode is not a gate. Diode
but
is not a
still,
gate.
I mean, it's a part of your combinational logic delay. So like,
what combinational logic does diode represent?
I mean, it just merely acts as a switcher, but like,
No.
if you
The
want to
diodes that I'm talking about here are so that due to fabrication, there could be a lot of ion deposition on your polysilicon gates, and you need to discharge them. Otherwise, the gate breakdown will occur. These are physical checks, technology linked checks.
Okay. Okay. Can you just elaborate on that further? I'm a little confused.
We will look at that in more detail later, but yeah, so when you manufacture silicon, you actually put very high energy, uh, you know, how do I put it, plasma onto your dies. Okay, this can lead to a lot of charge buildup on your dies, and that charge needs to be sunk into the substrate. Otherwise, there can be dielectric breakdown somewhere because of very high voltage.
Okay.
So every polysilicon gate needs to be connected to some drain or source, something like that, so that that charge has a path to discharge.
Okay, sir. Yeah. I
And if
understand.
there is none, you have to put a diode.
Yes. Okay. Okay.
Okay, so this is not a part of logic synthesis at all. Raghav, you also wanted to ask something?
Yes, sir. So this timing driven layout optimization, is it a part of like the routing part like that?
Yes. Placement, place and route. Yes.
Okay. And so one more thing. So this power estimation and the earlier power analysis that we done just after design entry, like estimation and analysis, does have a different connotation or like, or
Yes,
is
it
it about
has a
the
different.
accuracy?
It has a
Okay.
different connotation in the sense that when you did it the first time, you did not really have the exact numbers because you did not know the exact gates that would be used to implement your design. You just saw that, okay, this processor is being accessed 2000 number of times. Can I reduce it somehow? It was an architectural level thing. So this memory is being accessed every cycle. Can I reduce the number of accesses to the memory?
Okay. Okay. Okay, sir. And
But
so
now
one,
you actually have the power consumption that happens in every cycle, and now you're estimating it. And now you can tell, oh, I reduce it to 50%. Now I actually need to reduce it to 20% only.
okay, so at the power estimation, we are having the specific amount of power consumed at every cycle, like.
Yeah, because synthesis has happened. Now I know every
Yes.
device.
Yes, sir. And so one more thing, so that you have mentioned this clock synthesis before the flow planning. Generally, in a flow, we generally see that after done the placement and full planning and the placement, then we do the kind of this clock tree synthesis. But here
So
you have put before.
see, synthesis would happen alongside floor planning actually. So that is where the link is. So test and clock synthesis leads to two things: floor planning and this. But you see that is a horizontal connect, so it could actually be happening in parallel also. They feed into each other.
Okay, okay. So can you just briefly explain this, how these interconnections are made between the different boxes you have made? Actually, it's getting a bit like.
Yeah. So the ones, for example, static timing analysis, gate level synthesis, etc., they are all running in parallel. They do not. So while STA has something to do with floor planning and other stuff, gate level simulations has nothing to do with it. So in the STA box, I also show an entry of floor planning, but I do not show an entry of floor planning into gate level synthesis, for example. Okay. The output of STA goes for timing assertions. It also goes for SDF and RC and CAP estimation, and that information also come back to STA. So that is also shown as an input there and an output there. So if you look at these ones, these are reverse loops. That okay, if after STA I realize that something is not working, it means I will go back to this stage. I will redo the timing driven layout optimization. Okay, if I notice that, so when I release the netlist from here, I also release timing assertions so that they can be used for timing driven layout optimization. I release timing assertions to layout also. So these are not just one way, at least these ones over here. They may not necessarily be one way routes. They could be also both ways. Okay.
So timing assertions are basically the adjustment of the timing we are doing after the STA. So likewise, if some gate is failing or not.
Yes, you may say that this device is so far away from there that I need to put in some extra buffers in the other path.
Okay, sir.
Or bring these two devices closer. So that is the layout driven timing optimization
Sir?
section. Yes, Akshat?
So power estimation is done before timing optimization, as I can see in this.
Alongside. So you see
Alongside.
STA is happening alongside STA and
Mm-hmm.
power estimation are happening in the parallel plane.
So, sir, I want to know that power and load and idle power also matters.
Yes.
So after like I can see that before releasing to Foundry, there's no again power testing or something. Like when every optimization is done, every kind of optimization, there's no again power test or something.
Yeah. So what happens is, when you actually go into chip designing, you will notice that if you've done the gating and everything properly over here, and you've done verifications at gate level simulations and power estimation, then after the layout, not really much would change. Wires would change; they will reflect into STA. So as soon as you do this SDF and RF, you again come back to this level. So you do STA again, you may want to do some other checks of this place again. That can happen. But because there is some extra wire somewhere, because of that, power is not going to change from 1 milliwatt to 2 milliwatts. It may go from 1 milliwatt to 1.01 milliwatts.
Okay, sir.
Okay. Because you had used some wire load model even initially. And it is a fair, based on earlier products only. It's not a random thing picked up from somewhere. So many ICs have been designed till date that we have a fair amount of an idea that an IC of this complexity would use this kind of a wire load distribution. So power estimation does not really change much after this stage.
Okay, sir.
Because you already have the post layout library characterized, na? Okay.
So what is a wire load model?
A wire load model. Okay. So when I say that there are these many AND gates and these many NAND gates on a chip, they need to be connected, is it not? So there will be wires in between them. These wires will lead to loading of your gates. So what length of wire to assume between, or what length of wire to assume at the output of a given gate, that is probabilistically set through a model which is called as wire load model. Does that help?
So what is that block? What is that block in left corner? Like below
Sorry?
left corner.
Below left corner, SDF, RC, and CAP.
No, actually there is RC and cap block. Yeah. What is the function of that?
So after you have finally designed your entire chip, you will do a post layout extraction. So you will see now finally what are my capacitances at different places. And with those load capacitances now, is my STA, is my timing still correct or not? If it is not, you will go back to the STA stage and you will do a layout driven optimization all over again. So there will be ECO of some parts of your chip. ECO means engineering change order. So some things you will need to change so that your delays and everything are still intact. Okay.
And so the block which represents a test structure verification, is that connected to DFT and such things?
Yes. Yes. Raghav, you had a question. Your hand is raised.
Yes, sir. So this, can you just say there was a static time analysis and timing assertion? So what's the difference here?
Oh, so static timing analysis said that, okay, before the layout, I assume that there is some kind of a wire load on between the two, between the two gates. And I would say that this is what my timing is, because I assumed some load. Now, there could be some race conditions where the slack is very less. So you will tell that, oh, I do not really have margins here. So please do not increase the cap of this wire more than that. So what does that mean for the layout? It means that these two cells have to be placed close together. They cannot be kept far away.
Okay, so sir, it's kind of a directive for the optimization that do this, keeping this in mind.
Yes, they are timing assertions. Yes.
Okay, sir.
Madhur, you have a question?
Yes, so what's the difference between gate level simulation and test structure verification?
So gate level simulation would typically test only the functional modes. Okay. Test structure verification would typically test only the test modes.
I didn't get it. So what's the difference? What are the test modes? And I mean,
Yeah.
functional modes is the functionality that we expect. But what is the
So let us look at it like this. When I want to do a face recognition on an Apple chip, that is a function. I will test that face recognition and I will say this is working fine or not. However, for that particular chip, I need to keep a memory which is, let us say, 1 kilobit by 1 kilo words and 32 bits each word. 1K cross 32 memory I need to keep. During a functional mode, I may not actually access every memory cell, every memory location with both kind of data, 0 and 1. Let us say. So, but this was just the test program that you wrote. In reality, when the customer face would actually come, the any bit can be 0 and any bit can be 1. So for every memory, you have to test every bit for both 0 and 1. Your test cases may not have everything when you're designing test cases only for the functional mode. So you design a separate BIST, you add a built-in self-test into the overall system, which would access the memory for every location and write 0 and 1 on every location, so that everything is tested. Now, gate level simulation, you don't run the BIST, but in test structure verification, you will test the BIST. Does this help, Mother?
Yes, sir.
Okay. Gagandeep?
Sir, after the layout, when I want to go to STA, then I am necessarily changing the wire load models only, right?
So now you're not changing the wire load model. You're actually extracting the wire loads and putting that into the netlist.
Yes, sir. Changing the netlist wire load model from the
No, again, there is no model now, Gagandeep. Now this is the real thing that you're putting back in there. Model was an estimate. Model was an extrapolation. Now this is the real thing you're putting, real capacitance you're putting there.
Okay. Yes, sir.
Diveen?
Yeah, sir. So what you said about test structure verification, just to confirm, you're testing every single possibility. So,
yes.
right, isn't that kind of expensive? I mean, you're testing all.
So you tell me.
Like if you have
you enter into a car which was tested only for good road conditions. Would you drive that car?
So I mean, you have to make test conditions which will accommodate to every type of input.
So exactly. So that is what test structure verification is. But otherwise, gate level simulation is okay. My car is starting fine. It is receiving inputs from all the different sensors. It is working fine. That is gate level simulation.
So for example, when you're writing a computer code and you're testing it, right? So you might have like a million different test cases, but to accommodate each function, I mean, you only need a limited number of test cases, which test all the different possibilities. So doesn't this?
A test is a very, very significant cost. Okay. We will come to it. We'll come to it later in this in the next lecture. But test is a very significant cost. You actually have to test it very exhaustively.
So if in the gate level simulation, you're testing for those test specifications you have given, and then in test structure verification, you're testing each possibility. So what's the point of the previous step?
The point of the previous step is, okay, I just said that for memory, you have a BIST there. Okay. Now I tested the memory with the BIST. I know memory is functioning fine. Similarly, I test the processor with its logic BIST. All that logic is working fine. Do I not need to also test that the interface of memory and logic is working fine?
Yeah. Yes, sir.
Yeah. So that is what is the purpose of gate level simulation.
Okay.
That the functionality that you wanted, you are getting that.
Right.
Then
Right.
test structure is each component that you have put in itself is robust.
Okay, so gate level simulation is for the functionality, and then test structure verification is you're going into the fine details that okay, every single component is individually working fine.
Yes.
Okay.
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 So I have 3 people raising their hands. Madhur. Divin.
So the question was once again related to test structure verification. So in gate level simulation, we know that our circuit has this particular function. So in test structure verification, we are basically pushing it to its limits and finding out if there is any error.
Yes and no. So in a gate level simulation, I'm connecting the processor and the memory and all the different slaves of the processor and testing that everything as a system is working fine. In test structure verification, I'm putting the BIST into question and saying that is my memory working fine completely or not? Is my set of bank of flip-flops working fine completely or not? Given whatever input set.
Okay.
Okay.
So it's sort of like corner case testing.
Yes, it is something like, okay, मेरे को एक car बनानी है. I want to build a car. So at one point of time, I tested that the car starts and it runs well. Okay. And at another point of time, I tested just the engine separately, that it is giving me the horsepower that I require. And at another test, I'm testing only the tires that they are giving me the kind of grip that I require. So one thing was system level testing. The other thing is doing tests specific to the engine, so that I'm sure that engine will work even at minus 40 degrees Celsius and even at 125 degrees Celsius.
So like separate modules are being tested.
Yes. So one thing is more about module level testing and ensuring that every module is well tested. Okay. It also has some system level tests, but gate level simulation is more about functional testing. Okay. That all the required functionality is in there, is built in there. So once you have that, once you do, then finally you do the ATPG, automatic test pattern generation, and you release the stuff to the foundry. That okay, all my tests, all my timings, everything is closed. My power is within the budget. Everything is fine. Please fabricate it. Okay. And I tell you, each block over here is a kind of an independent job in industry. Each of these blocks is an independent job. Now, it may happen that there is a team that does all these 5 things. So there are people who are doing all these 5 things in one project or another. So they get exposed to all these 5 things. But it could also be in a particular case that one person is doing only this or this. STA hi kar raha hai wo bas. Post layout STA. That is the only thing he is doing. That can also happen. So each one of these is a specialized domain. So orange, yellow, and green could be different teams, or they could be actually independent jobs. Each block could be an independent job profile. Okay. So I think we should stop here. We will go to the abstractions levels in the next class. Okay. Any pending questions that you forgot to ask?
So I have one. So this after the yellow row, so mostly still we have not gone to the physical level.
No.
We are still at the logical level only.
Yes.
So but
after,
yes, sir. So but like in this after the static time analysis, you have connected it to the SDF, RC, and CAP. So what is that?
So SDF, RC, and CAP are inputs from after the layout has been made back into static timing analysis.
Okay, okay. So it's going the other way around, not
yes.
Coming from
arrow
up,
is on the other
below.
side. Yes.
So from the below, it's going up. Okay.
Yeah.
Okay. Okay.
Okay. So anything else?
So what kind of checks are done during pre-layout technology checks?
during pre-layout technology checks. Pre-layout technology checks, as I mentioned that, okay, even at the gate level netlist, the load of any one of my gates is not greater than 200 femtofarads. That is kind of a pre-layout. You don't even need to know the layout. You know that every gate has some input capacitance. So depending on what the fan out that you have connected, you can estimate the overall load on any particular gate. So these are like pre-layout technology checks. Quick estimates. Because if you need to do some buffering, you do it right away so that the netlist already has it and then you release it to the layout. Okay.